Okay, I've already mentioned to you in other presentations, unless you're watching this as the first in chapter 3, alkanes have very low reactivity. They have no functional groups, and so there's no place for other molecules to grab a hold of them and react, except one reaction. There's one reaction that they do, and that is they react with chlorine and bromine in the presence of light to replace one or more of the hydrogens with chlorines. The problem with this is it's a very uncontrolled reaction, and so what will happen is sometimes you have monochlorination, sometimes you have dichlorination, sometimes you have a mixture of all of these products being formed unless you have an excess of chlorine. And so the products of the reactions tend to be unpredictable. Well, they're not really unpredictable. They're very predictable, but it's a mixture, and so it's a mess. The physical properties of the alkanes are, first of all, they are oily and so not water soluble. But then one thing that we know is because the mass is increasing with the number of carbons, what happens to the boiling point is it steadily increases. So the boiling point of a 14 carbon alkane is around 250 degrees Celsius, whereas something like butane is just below 0 degrees Celsius. The melting points pretty much, there's a little bit of variability right here, but pretty much they increase with increasing molar mass or increasing numbers of carbons. Conformers are the positions of compounds as they rotate about single bonds. Single bonds have the ability to twirl around and around and never affect the energy of the sigma bond. So if I look at this molecule right here, these hydrogens can twirl around and around and around and around so that the hydrogens pass by, this hydrogen here can pass by this hydrogen and then this hydrogen and this hydrogen, rotating around very fast over and over and over again. Okay? Every single bond has that potential. So this is a change in the three-dimensional structure by bond rotation. So basically, this is like a little fan that would be twirling around and around and around. Now this right here is called a stick model representation. Some people call them sawhorse projections right here because you can twist this one in back so that it looks like a sawhorse. There is the Newman projection, which is much better at showing you how things line up. If I take this molecule and I take the front carbon that has the green hydrogens attached and I pull it up so that you're looking down the bond from this carbon down there so you can't see the carbon behind and all you can see is the carbon in front, it would look like this. This is the carbon in front, and these are the green hydrogens attached to it. And the carbon behind you can't see because it's behind this carbon. But these are the hydrogens attached to that carbon. If you have a model set and you don't understand this, build the model of 2 carbons with 6 hydrogens attached and play with it by looking down the bond and see if you can get to this representation. So the back carbon is not visible, and so what we do is we call this drawing right here a Newman projection. The circle in front represents the carbon in front, and these are the hydrogens attached to it. And the back carbon is invisible, where you can't see it, back behind the front carbon, and these are the hydrogens attached to it. Torsional strain is one of the strains that molecules have what we're going to do is we are going to talk about what is torsional strain first, and then we're going to see how this thing called torsional strain changes as the molecule changes its conformation. When you have the electrons in one bond get in the same plane as the electrons in another bond, those electrons see each other and repel. Because they repel, this makes it so that it's higher energy when those bonds become lined up with each other. This makes a barrier to rotation, and that some conformers have greater stability than the other. We're going to see that staggered conformation is
Here
most
we are
stable,
showing
and the eclipsed,
the different
eclipsed conformation is least stable.
of butane.
If I look at this conformation of butane, here's the carbon in front with a hydrogen up, over to the side, and over to the side. And then there's a carbon in back you can't see, but these are the hydrogens attached. If I look at this carbon-hydrogen and the carbon-hydrogen bond in back, you can see they are lined up. They're in the same plane. The electrons are going to repel each other, and so it makes it higher in energy. If I look down here, the back carbon has rotated, so now this carbon-hydrogen is rotated by 60 degrees, and it's between this carbon-hydrogen bond and this carbon-hydrogen bond. So this carbon-hydrogen set of bonding electrons is not in the plane with either this one or this one. This is lower energy. When we rotate it again, now these two are eclipsed, and so they're high in energy. Now all the hydrogens have a staggered conformation, so they're lower in energy. Eclipsed again, high energy. Staggered, lower. And you can see this goes on and on and on and on. Now the barrier to rotation is pretty darn small. It's 12 kilojoules per mole. So only at the incredibly low temperatures would you find that there is a barrier to rotation. This is so small that even at very low temperatures, the molecules have enough energy to overcome that barrier to rotation. All the other alkanes have that same torsional strain from bonds. So here is propane. Why is this propane? Because there's one carbon up here, a carbon in front, and then one behind that you can't see. That makes 3 carbons, so that's propane. So if I look at this, as this back carbon rotates, what would you find? As it rotates down this way, the bonds lined up and they're eclipsed. Then they become staggered. Then they line up and become eclipsed, and then they're staggered and then eclipsed. So what happens? The staggered propanes are lower in energy and the eclipsed are higher energy. See, here's lower energy. Here is higher energy. If I look at butane, I'm going to go and take butane right here, 4 carbons. Let's see why this is butane. There's a carbon here, a carbon in front, behind is a carbon, and then down below is a carbon. So that's 4 carbons altogether. Okay, now if I look at this, these are all staggered, right? Here's eclipsed, that's higher energy. So staggered, eclipsed, higher energy. However, there is another conformation that we see here, because this methyl group can either be opposite this methyl, or it can be up here and next to it. This conformation, when they're opposite each other like this, then what happens is lowest in energy because they're farthest away from each other. Because when I bring this methyl group up here, those carbon hydrogens start getting in the same space as these carbon hydrogens and they repel. So let's look at this. We have the anti-conformation, which is lowest in energy, shown on the previous page, and the methyl groups are 180 degrees apart. But then there's the gauche conformation, What is a gauche conformation? That's when they're adjacent to each other. And they are basically getting in each other's same space and they bump into each other. This is called steric strain, when the parts of molecules get close enough to each other that they bump into each other. So this will start to bump into this. It doesn't really look like it in this picture, but it does. And that's called steric strain. Here, the bonds are eclipsed. So we have torsional strain here. Here, there's no torsional strain because everything's staggered, but we have steric strain here. If I look at this, steric strain, now we have torsional strain because the bonds are lined up, and we have steric strain. So this is the least favored conformation of all, with the most resistance or highest energy, most resistance to staying there. Okay, let's put it all together. Here is anti, lowest in energy. As it rotates and the bonds become eclipsed, you have a methyl next to a hydrogen, very little steric there, steric interference, but we have torsional strain. Then, poop, we go to where it's staggered again, but now the methyl is close to the methyl, so it's higher in energy than the anti. This is called the gauche position. Right here, this is eclipsed with the methyls next to each other. This is the highest energy position of them all, right up there. Then it rotates a little farther, it's again gauche. The same energy as this one, because you have methyls close to each other, but no torsional strain from eclipsed bonds. Here, you have eclipsed bonds, but it's only methyl next to hydrogen, so you don't have this steric strain, and so it's lower in energy than this. And then down to the lowest conformation, which is the anti-conformation, which is staggered, no torsional strain, and the methyl groups are far apart from each other, so no steric strain. From this slide on, what we're going to be doing is problems that are from all of Chapter 3. So if you haven't watched the other PowerPoints in the Chapter 3 group, then you need to finish watching them before you try to do these problems. Okay, for this one, on each of these you try it, pause it before you hear the answer, and then restart it after you get your own answer. So this one is asking, what's the relationship between this and this? Here are the different possibilities. Don't worry about stereoisomers. You don't have to know anything about stereoisomers at this point in time. Okay, pause and then restart after you get your answer. Yes, if you look at these two, you will see that these are different conformations of the same compound. Why are they not constitutional isomers? For them to be constitutional isomers, what you have to have is different connectivity. The connectivity here is the same. There's a chlorine attached to a carbon, which is attached to the carbon behind, which is then attached to the chlorine. We have that same thing. Chlorine attached to carbon, which is attached to the carbon behind, which is then attached to the chlorine. What you do have, though, is that this is the anti-conformation of 1,2-dichloroethane, and this is the gauche conformation. If you look, I just twirl this up, this chlorine in back, up to this position right here, and I will get this conformation. So what is the relationship between these two? If you look at this, you will see these are constitutional isomers. This molecule over here is carbon in front, carbon behind with a hydroxyl group on it, and then another carbon. Right here there are 3 carbons in the molecule, but the hydroxyl group is on an N carbon, not on the middle carbon as in this one. So these are isomers. Okay, which is the least stable conformer of these 3 positions? If I look at this, you can see This is staggered and this is staggered. So these two are eclipsed. They've got to be higher energy. If I look at this one, the hydroxyl group is eclipsed with a hydrogen. Here, the hydroxyl group is eclipsed with another hydroxyl group. Here, we have torsional strain. Here, we're not only going to have torsional strain, but we will also have steric strain. Okay, which of these is the most stable conformer? If I look, I can see this and this are both eclipsed. So those are less stable than the ones that are staggered. Here, the groups are gauche. That's higher energy than when they're anti. So this is the most stable conformer. Okay, let's look at these functional groups. Which functional group is not present here? If I look, this is a carboxylic acid, so that is present. This is an alcohol. It is present. This is an amine. It is present. But there is, and there is a methyl group right there. So this is present, but there is no ketone. Do not mistake this as a ketone because it has a hydroxyl group attached. Whenever you have what looks like two functional groups on one carbon, it is not two functional groups, it's one, and they operate together, and here as a carboxylic acid. So what kind of carbon is not present in the molecule below? Primary, secondary, tertiary, quaternary? Or are all four of them present? A quaternary carbon is not present. Let's go through and look. Here we have a tertiary carbon. Here and here we have primary carbons. Here, 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 and here, we have secondary carbons. Right here, 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 and here, we have tertiary carbons. The only thing we don't see is a quaternary carbon, which would look like an X. Tertiary carbons look like a T or a Y. That's one right there. Secondary carbons look like a bent line. Primary carbons are the ends of lines. All right. How many secondary hydrogens are there in the following molecule? Remember that a secondary hydrogen is on a secondary carbon. If I look at how many secondary carbons are here, we have 1, 2, 3. Every secondary carbon must have 2 hydrogens on it, so the correct answer is 6. Which of the following choices is not an alkane? Well, figure this one out and then restart the lecture. If I look at this, I refer back to my understanding that an alkane has the formula CnH2n plus 2. So on all of these, all I do is I take the carbon number, multiply by 2, and add 2. This is 26, that's 2n plus 2. This is only 2n. This is 2n plus 2. This is 2n plus 2. And this is 2n plus 2. So the correct answer is this one. Okay, so we are looking for the number of secondary carbons and secondary hydrogens for an alkane. The chemist is having trouble deciding which of these numbers are correct. So which of these answers is possible for an alkane? Number of secondary carbons to number of secondary hydrogens. If I look at this, I remember that secondary carbons have 2 carbons and 2 hydrogens attached. So the number of secondary hydrogens has to be 2 times the number of carbons. So this cannot be, this cannot be, this cannot be, this cannot be, but this is correct. Double the number of hydrogens for the number of carbons when the carbons are secondary. What is the name for this compound here? go ahead and stop the lecture and figure out what the name is for this compound. Okay, if I look at this, I have to find the longest chain first. What is the longest chain? 1, 2, 3, 4, 5, 6, 7. So it's going to be a heptane, one of these two. What would be the possibility? Well, if I cross out what I considered the carbons that make heptane, I'm left with this and with this. This is a methyl, and this is an isopropyl group. It looks like a Pac-Man mouth that's been attached to a carbon. Okay, so if I look at this, 1, 2, 3 for the methyl, and then 4 for the isopropyl. How is it we list it? Both of these have 3 for methyl and 4 for isopropyl. We do it alphabetically. When we do it alphabetically, we don't consider dis, tris, and tetras, but we do consider prefixes that make things other than the straight chain. This is other than a straight chain, and the common name for it is isopropyl. So I comes before N, so this is the correct name. Okay, what is the systematic name of the alkane shown below? Go ahead and figure this out and then restart it. All right, in doing this, we find the longest chain and we can say, oh, it's 1, 2, 3, 4, 5, 6, 7, 8. But then we might say, oh, it's 1, 2, 3, 4, 5, 6, 7, 8. Which one do I choose? What you always do is choose the longest chain with the most substituents. If I go in this direction, I have 2 substituents. If I go in this direction, I have 3 substituents. So this is what I choose as my longest chain. Now, if I go ahead and look at the numbering, I can either choose to number from this end 1, 2, 3, 4, 5, 6, or I can choose to number from this end 1, 2, 3, 4, 5, 6, 7. If I number from this end 1, 2, 5, 6, it's a lower set of numbers. So I'm going to do that. So this would be 2, 6 dimethyl, and then this is the number 5 carbon, so that's 5 propyl. Make sure when you're counting that you do not count any of these chain carbons on your substituents. So this does not get counted with this. So this is only 3 carbons, not 4. This is only 1 carbon, not 2. This is only 1 carbon, not 2. So 2, 6 dimethyl 5-propyl octane is the correct name. Which of the following is not an isomer of hexane? Okay, hexane is C6H14. So now what I do is I have to find something with 6 carbons. This is 4 plus 2, so this could be. This is 5 plus 2. That's not an isomer with hexane. This is 5 plus 1 carbon. That's 6 carbons. So that is an isomer of hexane. This is 5 carbons plus 1. So that is an isomer of hexane. And this is 4 carbons plus 2. So this is an isomer of hexane. The only one that is not is this one. Go ahead and determine what is the name of the compound represented here. Each one of these is the same compound, so take any one of them and try to figure out what is the compound and name it. Okay, let's just go to this first one and look and see what is the longest chain. 1, 2, 3 carbons, 1 behind, that's 4 carbons, and then this one down here is 5 carbons. So that's pentane. Where's this methyl group? Well, if I count from behind, that's 1, the carbon behind, 2, and then the carbon in front, 3. Or I can count here, 1, 2, and then 3. And you can see it doesn't matter which direction you count, it's going to be 3-methyl pentane. if I look at these three conformations, determined which is the most strained, the intermediate, and the least strained or most stable conformation of all of these. Put them in order. If I look at these conformations, you will see that here I have one gauche interaction. Here I have one gauche interaction. Here I have two gauche interactions. So C is the least stable of all of them. Next, if I look, I can see that the biggest group is gauche to the methyl right here. Over here, there's a smaller group that is gauche to the methyl. So this is going to be the most stable. This will be intermediate stable. So it goes C, B, A, number 5. Okay, go ahead and read through these different statements about bond rotations and see which one of these is correct. It might take you a little time. Pause the lecture and read through them carefully. Let's take each one of these and try to find out which one is correct. Okay, rotation around a sigma bond is easy because orbital overlap does not change with rotation. This is correct. Because overlap is head-on. When the bond rotates, there's no change in that head-on overlap. Rotation about a pi bond, though, is not easy. The reason it's not easy is because when you start to twist that bond, it breaks the pi bond. So this is incorrect. Rotation around a sigma bond is very hard because the electron pairs from adjacent bonds must pass by each other. This is true that electron pairs from adjacent bonds must pass by each other, but it is not very hard. It's called torsional strain when you see bonds that line up, but it's not a huge resistance to rotation. It's a small resistance to rotation. Okay, rotation about a pi bond is hard because the electrons are delocalized. This is not true. That's not what causes rotation about a pi bond to be hard. Delocalization only occurs when you have resonance, and it has nothing to do with rotation about a pi bond. Rotation around a sigma bond is hindered because hydrogens on the adjacent carbons bump into each other. Well, there is torsional strain, but we don't have steric strain with hydrogens. Hydrogens are the smallest group that you can have, and we basically consider a hydrogen next to a hydrogen to not have any steric strain. Okay, which of the above representations is the Newman projection of 2-bromo 3-chlorobutane? You don't know how to name these things yet, so let me just tell you that 2-bromo butane has 4 carbons. 2-bromo means that on the number 2 carbon you have a bromo, and 3-chloro means on the number 3 carbon you would have a chloro. Go ahead and look and see if you can find the one that would represent this. This is pretty hard because it's not really included in our learning objectives for this chapter. So if you can't get the nomenclature, don't worry about it. But see if you can figure this out because it'll help to see if you understand Newman projections. Okay, if I look at this, you can see that bromine and the chlorine are on the same carbon. So this actually is 2-bromo 2-chloro. If I look at this, the bromine and the chlorine are on the same carbon. So it's 2-bromo 2-chlorobutane. If I look at this, this is carbon in front with a bromine, carbon behind with a chlorine, and then a methyl group. This looks like it's 2-bromo 3-chlorobutane. If I look at this, this is not butane at all because this is going to be a carbon attached to another carbon behind with 2 carbons attached to it. So this is a a methyl on a propane. And so it has a much different nomenclature than this. If I look at this compound, this again would be a propane with a methyl attached, because actually this is with an ethyl attached. Notice there's 1, a carbon behind, 2, carbon in front, 3, carbon here, 4, and then carbon there, 5. So this actually has 5 carbons and cannot be this at all. Okay, this is going to be a little bit of a time-consuming problem, so pause the lecture to try and do this. What is the energy difference between the 2 lowest energy conformations? So this is going to take some time because you have to first draw the Newman projection of 2,3-dimethylbutane. That's going to take a little time. Once you write that, then what you have to do is write all the different low energy conformations that you possibly can have. There's only 3 of them because as you rotate around, remember there's 3 different staggered positions. So you're going to be comparing 3 different staggered conformations, and then you're going to see what are the difference between the 2. When you get through trying this, I'm going to have a picture drawn for you, and I'll go through the explanation. Okay, here are the 2 low energy conformations. The 3rd low energy conformation is actually the same thing as this, but a mirror image of it. So the 2 low energy conformations actually have some variability. They're not the 2 highest are 3 gauche conformations anyhow. So let's go ahead and compare this one to this one. If you look at this, you can see the low energy ones, of course, have to be staggered. But if I look at how do I draw this, let's look and see. If I did butane, I would have carbon to carbon in front, then there's a carbon behind, then a carbon as the end of the chain. So that would be butane. Then I have to add 2 methyl groups to the 2 and 3 carbon. So 1, 2, there's a methyl group. And then 3 is behind, there's a methyl group. And then you can rotate this around to figure out the different conformations. This is the lowest energy conformation. What does it have? 2 gauche conformations. If I rotate this, punk, so that this methyl comes over here and this hydrogen goes up there, or if I rotate it so that this methyl comes down here and this methyl goes up there, they're the same energy either way. What you have is this over here. You've got a methyl that is gauche to this methyl, which is gauche to this methyl, which is gauche to this methyl. The difference in energy between these 2 is that this has 2 gauche interactions and this has 3 gauche interactions. So 1 gauche interaction is the difference between them.